at some stuff here. So I'm going to do the first page, hopefully quick. Thanks. Alrighty. So now on this part, going through off of our lab from the Pivot Interactives lab, and a couple of things. So we're getting tight on time. If you guys need to go, you can hang up and go. I understand this is taking me a little bit slow rolling. My apologies. So if you need to go, you need to go. I will try to go through and do a few of these questions to kind of explain what's going on. So if you're struggling with it, you'll be able to come back and take a look at this video later. I hope to have this video up around, I was going to say around noon, but I might make a couple of edits to fit things in. So I'll get this video up as soon as I can. And like I said, if you need to go, you need to go. Some folks are already hanging up. That's perfectly fine. I take no offense. I'm not judging in any way. As we're looking at this, we have the force and distance graph here. We've got force is A over D squared. We just looked at that in our slideshow a few minutes ago. Now, if we go through and read this, what I try to do is have text in here, and then I ask a question that just makes sure you read the text, just to make sure, because if there's no question, if it were me, I wouldn't read it very carefully. So it says, hey, here's our stuff. Note the line is more important than any individual data point. So down here, what's more important, the individual data point or the line? The line. That represents all data points. Then we have this. This talks about the stuff that we talked about in our slides. We have this delightful shape. If the distance gets doubled, the force becomes smaller than half of it. The force becomes much smaller. So we've got that, and the A in the equation accounts for everything that's not the distance between those two charges. This says, hey, force is distance, or pardon me, F is force, pardon me. D represents the distance between the charges. What does the A account for? Well, the A accounts for the amount of charge. The A accounts for the material between the charges. It accounts for both of those. So I'm going to say A accounts for all of those things. And if A, and I should maybe have not chosen A and B because we have the A above. This is saying a charge. We'll call that charge A or X or Z or Bob, whatever. We have a charge separated from this other charge by a distance D. The force represents the force that A exerts on B, or the force that B exerts on A, or the force F is both of them because the force that A exerts on B is the same as the force that B exerts on A. And this is just checking to make sure we are remembering that Newton's third law rule about interactions. It should be that one. Next. It's thinking. My clock says 11:31. Like I said, I'm going to try to go through some of these next questions are the parts where it gets really a little bit more challenging. If you have to go, you have to go, but I'll stick through and try to make sure that we can clarify some of these things. So here, this thing says there are two different charges. The left charge is pushing on the right. The right charge is pushing on the left. They're not in contact. They're just in an area, and their electric fields are interacting with each other. And the distance between the charges is just 1 millimeter, a fairly small distance. What is the force on the charge? Now, a couple of things first. I'm going to say a thing and then come back to the question. So the thing is that the forces that are here are way bigger than what they would be, or they're implying that the charge would be huge. I made these forces numbers that would be things that we're comfortable with. If they were numbers that were accurate for common charges, then we'd be using some different ways of writing down numbers, scientific notation and stuff, and it just gets kind of messy for really big or for really small numbers. So I made these numbers that we'd be comfortable with, and I just put in this little disclaimer, hey, the numbers are easy, but and they all work with the graph and with the equation, but they represent, and an abnormal or probably impossible amount of charge to be used. Maybe not impossible, but not something that we would be working with. So the numbers will work, but they're not realistic. So what we've got here, two charges pushing on each other. Those charges are 1 millimeter apart. What is the force on the charge? Well, if the distance is 1 millimeter, the force is up here. It's around 100. Quickie. There we go. And now we're saying that same graph, but now we're going to double the distance and go from 1 millimeter to 2 millimeters. What's the force on the charge? So if I double the distance, at 1 millimeter, the force was 100 newtons. At 2 millimeters, I'm going to change the mouse so it's more obvious what I'm doing again. So if I go from at 1 millimeter, the force was 100 newtons. At 2 millimeters, I doubled the distance. The force gets smaller, but it goes all the way down to about 25, right? At 1, it was 100. At a distance of 2, it's 25. So that's definitely a significant impact on the force. So now we're saying here, from question 1 to 2, we doubled the distance. We took the distance times 2. 2 squared is 4. Doubled the distance. So if I say 2d, 2 times d, 2 is squared, so 2 squared gives me 4. If we take the force for number 1 and we divide it by 2 squared, or we divide it by 4, how does our answer for number 1 divided by 2 squared compared to number 2? So what I'm trying to get at is that here we had a force at one distance, we had a force of 100. If I double the distance, I can divide the force by 2 squared, or 4. If I double the distance, the force becomes 1/4 as large. So it's kind of like saying A is the same, but now I change this from D to 2D, and then square that. So that's like 1/4. This force is 1/4 as much. 100 divided by 4 is 25. We doubled the distance, and we got 25 newtons. So they should be the exact same. Now here, the charges are initially 1 millimeter apart. We move them so that the distance is tripled. So now we're to 3 millimeters. At 3 millimeters, we started at 1 and had a force of 100. If we triple the distance and go to 3, now our force is, it looks like it's a little bit more than 10. It's less than 15. So it's between 10 and 15, looks like to me. And 11 is between 10 and 15. Yeah. All right. So we tripled the distance. We went from d equals 1 to d equals 3. And our force went way down, right? Not just divided by 3. 100 divided by 3 is like 33. This is less than that. In fact, if we take 100 and don't divide it by 3, but if we divide it by 3 squared, 100 divided by 9, then we're right around that 11 point, right? So if we triple the distance, the force should be reduced to 1/9 of its initial value. And now when we look at this one is strange. I was trying to come up with a way to show what things with force arrows and things. So this one in the past, last quarter, we had to kind of spend some time looking at this. So what I'm trying to say here is that we have this charge and this charge that are interacting. They're at a distance d, and the force on this charge is 9F. So when these two are a distance 1d away, the force on them is 9F. Now, if we go to a distance that's triple that, that's 3 away, a distance of 3d away, what would be the force on the object when we put the charge here? Well, if we triple the distance, the force should be 1/9 what it was. So if this is 9F at a distance of 1D, when our distance is 3D, it shouldn't be 3F, that's 9 divided by 3. It shouldn't be 9 divided by 3. It should be, we're tripling the distance. It should be divided by 3 squared. It really, we're looking at this. The force becomes much, much, much smaller. If it's 9F at a distance D away, at a distance 3D away, it's just F, 1F. I hope that makes a little bit of sense. I'm trying to find different ways to connect these things. And then here we're on to a spot where we say, now I think we move to 4. Yeah, so the charges are initially 1. We move them to 4 millimeters away. So read the graph. What's the force when they're 4 millimeters away? Well, at 4 millimeters here, between these two lines. So at 4 millimeters, it's between 5 and 10 newtons, which is 6, right? 4 is less than 5. So there we have it. And if we take 100 and we divide it by not 4, sorry, take a step back. At a distance of 1, the force was 100. If we increase the distance by a factor of 4, we increase our distance to 4D, the force should be reduced to 1/16 of that value. So if I take 100 and divide it by 16, we should be getting something right around 6 newtons. And clicked on next to get the next screen. Alrighty, and then this is more of the same sort of stuff. So different amount of charge. So we have the same sort of setup, but we have 2 different amounts of charge. So our curve is going to be a little different. We have a different amount of charge. What's the force, the electrostatic force on these charges when they're a distance 1 apart? Well, when the distance between the charges is 1, it looks like the force on those 2 charges is 90, about. There we go. And now I'm going to say, hey, initially it was a distance of 1. Now we're going to triple the distance to 3. So at a distance of 1, it was 90. At a distance of 3, it's now about 10. Just reading the graph, right? And now when we tripled the distance, what happened to the force on the charges? So when we tripled the distance, it went from 90 newtons all the way down to 10 newtons. So when the distance was tripled, the force didn't get bigger, it got smaller. So it definitely wasn't tripled. When the distance was tripled, the force was reduced to 1/3. Well, if the force was reduced to 1/3, 90 divided by 3 would have been 30, and that's not what we got. So it's definitely not the first choice. It's not tripled, it's not 1/3. If it was 1/6, that doesn't quite work out either. If the distance was tripled, the force was reduced to 1/9. So if we initially at 1, it was 90. At 3, it was about 10. So 10 is 1/9 of 90. So it's reduced, if we double the distance, it's reduced to 1/2 squared of its value, or 1/4 of its value. If we triple the distance, then it's reduced to 1/9 of its value. Last part, I think. Maybe not, there's 2 more things down there. Bloop, 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 bloop. T. Alrighty. And then this is more of the same sort of stuff, right? Okay. Different amount of charge again, new curve. So what's the electrostatic force when the distance is 2? So I can just read, when the distance is 2, the force on those charges is roughly 20. Clicky. If we double it from 2 to 4, double the distance, pardon me, from 2 to 4. At 4, it's less than 10, and that looks about halfways-ish. So I'd say maybe 5-ish. 5. So we doubled the distance from 2 to 4, and we went from 20 down to about 5. Doubling the distance from 2 to 4, when the distance is doubled, what happened to the amount of force on the charge? When the distance between the charge doubled, the force also doubled. That means that if the distance increased, the force increased. Definitely not that. When the distance doubled, the force decreased to half its value. Well, we started at 20. Half of that would have been 10. And we weren't at 10 when we doubled the distance. So it didn't go half of it. When the distance doubled, the force was reduced to 1/4. Well, it went from 20 down to about 5. 20 divided by 5 is 4. It is, yeah, it is 1/4 of its original value. That works. And then these next couple spots are just, I think, real quick summary. So the reason that we're focusing on this is it's kind of an unusual thing. It feels like it's an unusual thing, but there are a lot of things in the world that follow this 1/x² sort of a relationship. People will often call it an inverse square relationship. Electric fields, gravitational fields, magnetic fields, light intensity, some issues dealing with intensity of earthquakes and things like that. Nuclear radiation things, a lot of things follow this inverse square relationship. So it's worth taking a little bit of time to see it in some way in class. Next, and this is just saying, hey, when you're done, you should be able to click on some things, see your score, and decide if you want to resubmit and make some changes. So there you go. That's a lot longer than normal class is intended to be, but we've got everything there. I'll try to break this off into sections, so if people want to take a look at it later, it won't be that long of a chunk. Have a good one, folks.